Okay, in this video, we're going to talk about section 5.2 dealing with integration by substitution. And in this section, we're going to reverse the chain rule to find indefinite integrals. Also, we'll use the method of substitution to find indefinite integrals and solve applications involving antiderivatives that require substitution. All right, so basically, when we do integration by substitution, we're going to be doing something called reversing the chain rule. All right, now, if you recall that the chain rule is this: if you have the derivative with respect to x of f of g of x, where g of x is your inside function, the outside function is f of x, we do this. We take the derivative of the outside function f prime of g of x, and then we turn around and take the derivative of our inside function, which is going to be g prime of x. So the expression on the right is formed from the expression on the left by taking the derivative of the outside function of f and multiplying it by the derivative of the inside function g. So if we recognize an integral as a chain rule form, f prime of g of x times g prime of x, we can easily find the inside derivative of and its indefinite integral. So here it is. The integral of f prime of g of x times g prime of x dx will be equal to f of g of x plus c. Okay. So that's how we can find the antiderivative and its indefinite integral. All right, now here's some formulas for the general indefinite integral functions here. The first one is, of course, the power rule when we're dealing with the chain rule, the reversing of the chain rule. The integral of f of x and that quantities to the nth power times f prime of x dx would be this. We just take the f of x function, increase the power by 1 divided by the new exponent, and then plus c. Restriction there is that n, which is your exponent, cannot be equal to -1. And we pretty much talked about that in the last video, where this restriction of n not equaling to -1. Number 2, e, the integral of e raised to the f of x, where f of x is some function, times f prime of x dx will just be e raised to the f of x plus c. Then the third rule is the integral of 1 divided by f of x times f prime of x dx would be the natural log of f of x plus c. So these are similar to the rules that we talked about in the previous section 5.1 dealing with antiderivatives and indefinite integration. But here we're just introducing a function in terms of x. So in the first example on the next page, we're just going to apply those formulas here. So like in part A, we got the integral of 2x cubed minus 3, and that quantity is to the 20th power times 6x squared dx. All right, now it does follow rule number 1, where you have, in this case here, this part is f of x, and that's raised to, in this case, the 20th power. Now that's 6x squared dx. That's actually f prime of x, because if you take the derivative of 2x cubed minus 3, you're going to get 6x squared. All right, so to find this integral using rule number 1 that we have here, what I'm going to do here is take that 2x cubed minus 3, increase the power by 1, so we add 1 to the 20, you'll get 21. Now it'll be divided by 21, and then plus c. Now, another way we can write that would be something like this. I'll say 1 over 21 times the quantity 2x cubed minus 3 raised to the 21st power plus c. So all I'm doing there is applying rule number 1 on the previous page to this problem. All right, now look at part B. You got the integral of e to the 5x times 5 dx. Well, that follows rule number 2. Whereas the integral of e to the function f of x times f prime of x dx, that's going to end up being e to the f of x plus c. Okay, so now, if I had the integral of, let's say, this part right here, e to the x, e to the 5x, that's like e to the f of x times, and that 5 is like f prime of x dx. Excuse me, because if you take the derivative of 5x, you're going to get 5. That part is your f prime of x. So we're going to end up getting e to the f of x plus c. So this will be just e to the f of x, which is your 5x, plus c. And that's all there is to that problem. All right, now part C, we got the integral of 1 over 4 plus x squared times 2x dx. Well, that follows rule number 3, formula number 3. The integral of 1 over f of x times f prime of x dx. That would be the natural logarithm of the absolute value of f of x plus c. So in this case, now let's think about this here for a moment. This 1 over 4 plus x squared, that's the integral of, in this case, 1 over f of x. And then the 2x dx would be f prime of x dx. And that's because if I take the derivative of 4 plus x squared, I would get 2x. So that means this will be the natural log of the absolute value of 4 plus x squared plus c. Now, in some cases, they don't use the absolute value here because if you notice, 4 plus x squared, that's never going to be negative. So sometimes they can write that without the absolute value. Sometimes they'll write it as ln of, in parentheses, 4 plus x squared, and then plus c. But either one of these is correct. Okay. So that's how we use those formulas for the general indefinite integral functions to find its integration. All right, so now let's talk about integration by substitution. Recognizing the integrand forms for formulas 1, 2, and 3 is key to using the formula. But when these forms are not obvious, the method of substitution can be used to simplify the integrand to determine if the form fits the use of one of the formulas. Okay, so the method of substitution becomes increasingly useful as one progresses in the studies of integration. We start by introducing the idea of the differential. We represent the derivative by the symbol dy dx taken as a whole. We now define dy and dx as two separate quantities with the property that their ratio is still equal to f prime of x. All right, so here is the definition of differentials here. If y is equal to f of x is a differentiable function, then the differential dx of the independent variable is any arbitrary real number. And then number 2, the differential dy of the dependent variable y is defined as this. dy is equal to f prime of x dx. Okay. So on the next page here, you'll see example 2. Here we're going to be dealing with differentials here. So in example 2, part A for dy, find dy for y is equal to f of x equaling to x cubed. So y is equal to x cubed. So when we find dy, we just take the derivative of x cubed. That's going to be 3x squared. And then we include dx. For the derivative of x cubed, of course, you bring the exponent down using the power rule. Copy the variable over to the 1 less power, so it'll be 3x squared dx, which is what dy will be equal to. And in part B, you're going to find du for u is equal to h of u equaling to the natural logarithm of the quantity 2 plus x squared. Okay, so in this case here, when we find du, we take the derivative of ln of 2 plus x squared. That's going to be 1 over this expression 2 plus x squared. But then we're not done. We have to take the derivative of the inside function, the derivative of 2 plus x squared. The derivative of 2 is 0. The derivative of x squared will be 2x. So I got 1 over 2 plus x squared times 2x. And of course, we need to include the dx. And we can simplify this as, let's say, 2x in the numerator divided by 2 plus x squared dx. So that's what du will be equal to 2x over 2 plus x squared dx. And in part C, you're going to find dv for v is equal to g of t equaling to e to the negative 5t. So dv is this. The derivative of e to the negative 5t, well, that's the easiest derivative to take. That's going to be e to the negative 5t. But then we got to multiply that by the derivative of this function right here, negative 5t. The derivative of negative 5t would be negative 5. And of course, we add the dt behind it. So if I simplify this a bit, I'm going to have the negative 5 times e to the negative 5t dt. Okay. So that's how we find those differentials. Okay, now the substitution method is also called the change of variable method since u replaces the variable x in the process. Substituting u equal f of x and du equaling to f prime of x dx in formulas 1, 2, and 3 produces the general indefinite integral formulas 4, 5, and 6. Okay. And forgive me for not having these numbered correctly. But these are the general indefinite integral formulas using a u substitution, as I call it. So here the integral of u raised to the n du would be, of course, bringing over the u, increasing the power by 1, divided by the new exponent n plus 1, and then plus c. The restriction again, n is not equal to negative 1. And then the second one would be the integral of e to the u du. That's going to be equal to e to the u plus c. And then the third one, the integral of 1 over u du would be, of course, the natural log of the absolute value of u plus c. Now, these formulas are valid if u is an independent variable, or if u is a function of another variable and du is a differential of u with respect to that variable. So here the substitution method for evaluating certain indefinite integrals is outlined as follows. So here's the procedure for that. Number one, you're going to select a substitution that appears to simplify the integrand. In particular, you want to try to select u so that du is a factor of the integrand. And then step number two is to express the integrand entirely in terms of u and du. That is completely eliminating the original variable. And then step number three is to evaluate the new integral if possible. And then step number four is to express the antiderivative found in step three in terms of the original variable. Okay, so we're going to be applying this procedure to some of the examples that I have for you in this video. All right, so let's start with example 3. Here I'm going to use a substitution to find each indefinite integral. In this case, you have the integral of the quantity x squared minus 3x plus 7 raised to the 4th times 2x minus 3 dx. Okay, so here I'm going to select a u so that du will be the factor of the integrand. And I'm going to start with this one right here, that x squared minus 3x plus 7. That's the part that's inside the parentheses. I'm going to let u equal to x squared minus 3x plus 7. And then I'm going to find out what du is. I can take the derivative of this u function. The derivative of x squared minus 3x plus 7, well, the derivative of x squared will be 2x. The derivative of minus 3x will be minus 3, and the derivative of plus 7 will be 0. So du is equal to 2x minus 3, and I need to include dx after that. Now notice I've already got 2x minus 3 dx. So here I can go ahead and make that substitution into this problem here. So this 2x minus 3 dx is the du. And here this is going to be u for the x squared minus 3x plus 7. So that means using the appropriate u substitution, I'm going to have this, the integral of, replace this with the u, so the integral of u, and this is to the 4th power, so I need to put that as u to the 4th, and then that 2x minus 3 dx will be du. So here I got the integral of u to the 4th du. Now, let's apply the power rule by increasing the power by 1 divided by that new exponent. So if I increase that 4 by 1, if I add 1 to the 4, I'm going to get 5, so it'll be u to the 5. And that's going to be divided by that new exponent of 5. And then, of course, since it's an indefinite integral, I must include the plus c. Now, we're going to express that antiderivative in terms of the original variable. That means I need to do some back substitution. Since I let u equal to x squared minus 3x plus 7, I'll replace that u, the u, with that expression, x squared minus 3x plus 7. And that's going to be raised to the 5th divided by 5, and then plus c. Now we could write this as 1/5 times the quantity x squared minus 3x plus 7 raised to the 5th plus c. Okay. All right, so that's how we do integration by substitution. Okay, here's another example. Here we're going to use a substitution, use a u substitution to find each indefinite integral. So in part A of example 4, we got the integral of 2x cubed minus 3 raised to the 4th times 6x squared dx. So here I'm going to use an appropriate u substitution. So in this case here, I'm going to let u equal to what's inside the parentheses here, that 2x cubed minus 3. Then I'm going to take the derivative of that. So du in this case would be, the derivative of 2x cubed would be 6x squared. The derivative of minus 3 will be 0, so it'll be 6x squared dx. And notice I do have 6x squared dx already. So this right here is my du, and that 2x cubed minus 3 is going to be u. So now using the appropriate substitution, I have the integral of u raised to the 4th times du. And just like in that last example that I just did, we increase the power by 1, so it'll be u to the 5th divided by that new exponent of 5 plus c. And I'll write this as 1/5 times, replace the u with that 2x cubed minus 3. And that's going to be raised to the 5th power plus c. So my final answer there would be 1/5 times the quantity 2x cubed minus 3 raised to the 5th plus c. And in part B, that's pretty much similar to one of the examples that I've already did in example 1, but only thing different here is the variables change. The integral of e to the 5w times 5 dw. Now we're going to use that substitution by letting u equal to the exponent for the e, which is 5w. And then the derivative of u, du, will be, the derivative of 5w will be 5, but this is in terms of w, so I have to include dw, which is exactly what I have here, 5 dw, because that right here, this right here is du, and I'm letting u equal to 5w. So using the appropriate u substitution, this will be the integral of e to the u du. And that's the easiest integral to take, because the integral of e to the u du is simply just going to be e to the u, and then plus c. And then I'm going to replace that u doing the back substitution with the 5w, so it'll be e to the 5w plus c. And that is what that integral will be, e to the 5w plus c. All right, now let's look at some additional substitution techniques. In order to use the substitution method, the integrand must be expressed entirely in terms of u and du. In some cases, the integrand must be modified before making a substitution and using one of the integration formulas. Okay, because some cases it's not always going to be where you can just directly do a u substitution. Sometimes you may have to modify it just a bit. And here's some examples of that. Let's say I wanted to integrate this. In part A, I have the integral of e to the negative 3x dx. E to the negative 3x dx. So here's our substitution. So here I'm going to let u be that exponent for the e, which is negative 3x. And then when I take the derivative of that, du would be, the derivative of negative 3x is just going to be negative 3. Then I'm going to include the dx. Well, here's the problem. I do have a dx, but I don't have a negative 3 in front of that. So I'm going to modify du equaling to -3 dx by getting dx by itself. Since it's being multiplied by 3, I'm going to divide both, by -3, I'll divide both sides by -3. So that means that I'm going to have -1/3 du equaling to dx. All right, so now here's where the substitution comes in. That -3x for that exponent, that's what will be equal to. This dx would be replaced with that -1/3 du. So I'll have the integral of e to the u times dx. Dx will be, in this case, -1/3 du. And -1/3 is a constant, so I can pull the constant out in front, so it'll be -1/3 times the integral of e to the u du. And then I can integrate this as, bring down the -1/3, the integral of e to the u is e to the u, and this is an indefinite integral, so I must include the plus c. So now u, of course, I'll do the back substitution, that's -3x, so here I'm going to have -1/3 e to the -3x, and then plus c. And this is what the integral of e to the -3x dx will be, -1/3 e to the -3x plus c. Right? Now, part B is this. Here we got the integral of x divided by x squared minus 9 dx. So here we're going to integrate by substitution in this case here. So what I'm going to do here is let u, and I'm going to take the denominator of x squared minus 9. Let's use that. Because sometimes you have to take probably the most complicated expression and let that be u. So you have to try something here. So I'm going to let u equal to x squared minus 9. And then take its derivative. So that means that du is equal to, the derivative of x squared would be 2x. And the derivative of minus 9 is 0. So du would be equal to 2x dx. Now, I do have an x and a dx, but I don't have the 2. So what I'm going to do here is come up with an expression with just x dx in it. So that way I can make the appropriate substitution. Here I'm multiplying it by 2, so let's go ahead and divide both sides by 2. So I'll have x dx, that's going to be equal to, let's say, 1/2 du. So 1/2 du will be equal to x times dx. Now let's go ahead and make the appropriate substitution here. So in this case here, this would be the integral of x times dx would be that 1/2 du. This would be divided by x squared minus 9. That's going to be what u is. So I substitute everything so that way I have an integral in terms of u. Now that constant of 1/2 I can pull on the outside, so it'll be 1/2 times the integral of, I'm going to say 1/u du. Now if I bring over the 1/2, if I integrate 1/u du, that's going to be, if you recall, the natural log of the absolute value of u, and then plus c. So I have 1/2 the natural log of the absolute value of u plus c. Now let's do the back substitution because I have to give my final answer in terms of x. So it'll be 1/2 the natural log of, u was the x squared minus 9. and then plus c. So my final answer there would be 1/2 the natural log of the absolute value of x squared minus 9 plus c. Okay. All right, part C looks like this. The integral of 5t squared times the quantity t cubed plus 4 raised to the -2 dt. All right, so now we need an appropriate u substitution here. So I'm letting that t cubed plus 4 be u. So I'm going to let u equal to t cubed plus 4. Let's find this derivative of u. So that means du will be this. The derivative of t cubed would be 3t squared. The derivative of 4 is 0. So du then would be 3t squared dt. Now notice here I have a t squared and a dt, but I don't have a 3. So let's write this in terms of just t squared dt. It's being multiplied by 3, so I'll divide both sides by 3. So I'm going to have 1/3 du is equal to t squared dt. All right, so now, when I do the u substitution, notice that 5 is a constant. I can pull the 5 on the outside. So it'll be 5 times the integral of, and I'm going to rewrite this as, let's say, t cubed plus 4, and that quantity is to the -2 times t squared dt. So now I have 5 times the integral of, now here's what I'm going to do the substitution. That t cubed plus 4 is what u will be equal to. So I know that I'm going to have u to the -2. And then t squared dt, that's going to be what 1/3 du would be. Now, here 1/3 is a constant. So that means if I take the 1/3 and multiply it by 5, which will be 5 over 1, so it'll be 5 over 1 times a third will be 5/3. So it'll be 5/3 times the integral of u to the -2 du. Now, in this case here, I have to use the power rule by increasing the power by 1, dividing it by that new exponent. So in this case here, bring down the 5/3. If I increase this by 1, it'll be -2 plus 1, which will be -1, divided by that new exponent of -1 plus c. Now, that 5/3 divided by -1, that's just going to be -5/3 here. And if I replace the u with that t cubed plus 4, I'll go ahead and do that. That'll be t cubed plus 4, and that quantity is to the -1 power plus c. Now, in this case, I'm going to write this using positive exponents, so I'm have a -5 over the 3 will be in the denominator. That t cubed plus 4 will be in the denominator as t cubed plus 4 to the +1 plus c. Okay. So that's how we find the integral of this using an appropriate u substitution. Okay, now on the next page, sometimes it's not going to be possible to find a substitution that makes the integrand match one of the integration functions exactly. So a substitution may simply simplify the integrand sufficiently so that other techniques can be used. All right, now take a look at example 6 here. You're asked to find the integral of x times the square root of x plus 1 dx. Okay. Now we can use an appropriate u substitution by doing this. I can let u equal to what's underneath this radical, dx plus 1. Then if we take its derivative, du will be, the derivative of x will be 1. The derivative of 1 would be 0. So I have du is equal to 1 dx, or just dx. Well, I do have that, and I can replace the u with the x, the x plus 1 with the u, but I need something to replace with this x, because the whole integral has to be in terms of u. And I need to find something to replace this x with. Well, let's look at this. We already know that u is equal to x plus 1. Well, let's write this in terms of x. Let's solve this equation in terms of x. We're adding 1, so that means I need to subtract 1 on both sides. So that means x will be equal to u minus 1. So let's use that u minus 1 and replace that in terms of this x right here in this integral. So here's what we got. We got the integral of, this x is being replaced with u minus 1. And I'll go ahead and say this here. This is going to be u minus 1. That x plus 1 would be replaced with the u. The dx would be replaced with du. Okay, so I got the u minus 1 being replaced for x times the square root of x plus 1 that's being replaced with the u, and then x will be du. Now, let's simplify this. I'm going to bring down u minus 1, the integral of u minus 1. I'm going to write the square root of u using rational exponents. That would be u to the 1/2 power du. Because if you remember the square root, the exponent for the u is the understood 1. This index here is the understood 2. That would be your denominator. So the square root of u will be u to the 1/2 power. Now, if I use a distributive property, u to the 1/2 times the u, that's going to be u to the 3/2. If you multiply powers of the same base, you add the exponents. That means this understood 1 will be added to the 1/2. It'll be 1/2, but as an improper fraction, it'll be 3/2. And then minus u to the 1/2 times the 1 would just be u to the 1/2. And then du. Now we can integrate each expression, because the integral of a difference would be the difference of the individual integrals. So it would be the integral of u to the 3/2 du minus the integral of u to the 1/2 du. So for the integral of u to the 3/2 du, we increase the power by 1. So it'll be 1 plus 3/2. It could be 1 3/2, but if you change that to an improper fraction, it will be 5/2 divided by that new exponent of 5/2 minus, for the integral of u to the 3/2, we increase the power by 1 as well. So it'll be 1 plus 1/2, or 1/2. As an improper fraction, it'll be 3/2 divided by that new exponent of 3/2. And of course, we have to include the plus c. Now, the reciprocal of 5/2 is 2/5. So I'm going to write that as 2/5 times my u was x plus 1. So I'm going to replace that u with the x plus 1, and that's raised to the 5/2 minus the reciprocal of 3/2 will be 2/3 times the u. Again, that's going to be replaced with x plus 1 raised to the 3/2 plus c. and I will go no further than this. So my final answer there would be 2/5 times x plus 1 to the 5/2 minus 2/3 times x plus 1 raised to the 3/2 plus c. All right, here's another example just like that one. Here we're going to use substitution to find the indefinite integral, like the integral of p times the quantity p plus 9 raised to the 4th dp. So here we're going to use the substitution here. I'm going to let u equals to what's inside this parentheses, p plus 9. Let's find this derivative. So du would be equal to, well, the derivative of p is going to be 1, and the derivative of 9 is 0, so it'll be 1. And then we include dp, which is, of course, dp. So du is equal to dp. Well, we'll let u be this. dp will be du, but I need something for p to be in terms of u. So that way, the entire integral will be in terms of u. Well, let's take the fact that we let u equal to p plus 9. Let's go ahead and solve this for p. That way, we'll substitute that in terms of u. Well, p is being added. We're adding 9 to p, so we need to subtract 9 on both sides. So it'll be u minus 9 equaling to p. So that's what p will be equal to, u minus 9. So this p, we'll substitute that with u minus 9. That way, we're going to have the integral of p is replaced with the u minus 9 times p plus 9 is being replaced with u, but it's going to be u to the 4th times du. And by the way, that is a 9. Now, in this case here, we can use the distributive property. So distribute the u to the 4th over the u minus 9, you're going to get this. The integral of u to the 4th times u to the 1st, that would be u to the 5th. And then u to the 4th times the minus 9 would be minus 9 u to the 4th times du. Now we can integrate each expression, so that means this will be the integral of u to the 5th du minus, now since the 9 is a constant, I can pull the 9 out in front as 9 times u to the 4th du. So now let's integrate each expression here. So for the integral of u to the 5th, we increase the power by 1, so it'll be u to the 6th divided by 6. Then minus 9 times, increase the power by 1, so it'll be u to the 5th divided by 5. And then plus 6. Now, if I do the back substitution by replacing the u with that p plus 9, because the answer has to be in terms of p, this will be 1/6 times u, which is p plus 9. That's raised to the 6 minus 9 over 1 times 1/5 will be 9/5. And replace the u with that p plus 9. And it's going to be raised to the 5th and plus c. Keep in mind, with all your indefinite integrals, you must include the plus c behind it. Okay. All right, on the next page, example 8. Here we're going to find the indefinite integral. Here we're going to be finding the integral of e to the 5x times the quantity 5 plus e to the 5x raised to the 4th dx. So here we're going to be using an appropriate u substitution here. So here I'm going to let u equals to what's in this parentheses here, 5 plus e to the 5x. And then du would be this. The derivative of 5 is 0. The derivative of e to the 5x, that's going to be, in this case, e to the 5x, but then we got to take its inside derivative. The derivative of 5x would be 5 times dx. So if I simplify this, du would be equal to 5 e to the 5x dx. Excuse me. Now, let me go ahead and rearrange these terms here in this integral. So here we've got the integral of 5 plus e to the 5x, that quantity is to the 4th power, multiplied by e to the 5x dx. Notice I do have e to the 5x, but I don't have a 5 there. Let's write this with just e to the 5x equaling to something. Here, since e to the 5x dx is multiplied by 5, let's divide both sides by 5. So I have e to the 5x dx is equal to 1/5 du. So now let's go ahead and do our substitution here. That 5 plus e to the 5x, that's what u is. E to the 5x dx will be that 1/5 du. So I have the integral of u raised to the 4th times 1/5 du. And since 1/5 is a constant, I can pull the constant out in front of the integral sign, so it'll be 1/5 times the integral of u to the 4th du. And then integrate u to the 4th by increasing the power by 1. So it would be, in this case, 4 plus 1 would be 5, so it'd be u to the 5th divided by 5, and then plus c. Well, 1/5 times 1/5 would be 1 over 25. And then replace the u with that 5 plus e to the 5x. So it'd be 5 plus e to the 5x. That quantity is to the 5th power. And then plus c. So the final answer there will be 1/25 times the quantity 5 plus e to the 5x raised to the 5th plus c. And then here's an application problem that deals with integration by substitution. And it says this: the weekly marginal cost of producing X pairs of tennis shoes is given by the following function, where C of X is the cost in dollars. So here we got C prime of X equals to 10 plus 200 divided by X plus 1. If the fixed costs are $400 per week, find the cost function. What is the average cost per pair of shoes if 1,000 pairs of shoes are produced each week? Okay, so the first thing I need to do here, this is what C prime of X is. So to find the cost function C of X, I have to take the integral of C prime of X dx. And that's the weekly marginal cost of producing X pairs of tennis shoes. And C prime of X is at 10 plus 200 divided by X plus 1. So I replace that with the 10 plus 200 divided by X plus 1 dx. Now here I can integrate each piece, each term. So this will be the integral of, say, 10 dx plus The constant of 200 I can pull on the outside as 200 times the integral of 1 over x plus 1 dx. Now for this, we can use an appropriate u substitution. So here I'm going to let u equal to the denominator of x plus 1. Then that means du would just be equal to 1 dx, or just dx. The derivative of x is 1 and the derivative of 1 is 0. So du then will be equal to dx, which is exactly what I have here. So I'll do this. Bring down the integral of 10 dx plus 200 times the integral of 1 over u du. X plus 1, I'm letting u be that. Dx came out to be du. Now let's do some integration here. The integral of a constant times dx will just be that constant, and we just tack on the variable x. So the integral of 10 dx will be 10x plus 200. And the integral of 1 over u du would be the natural log of the absolute value of u. And of course, we're dealing with an indefinite integral. We'll add the plus c. All right, so I'm going to replace that u with that x plus 1 because I want that cost function to be in terms of x. So it'll be 10x plus 200 ln of the absolute value of x plus 1 plus c. Now, we are told that the fixed costs are $4,000 per week. That means if no tennis shoes are produced, no tennis shoes are produced, that means the cost is $4,000. So that means x can be 0, and that would mean c of x would be $4,000. So this is what c of x is. And I'll replace that with the 4,000. So it'll be 4,000 equaling to x is 0. So I substitute each x in this with 0. So it'll be 10 times 0 plus 200 times the natural log of the absolute value of 0 plus 1, and then plus c. So I got 4,000 equaling to 10 times 0, that's 0, plus 200 times the natural log of 1 plus c. And if you were to do this in the calculator, the natural log of 1, or if you remember from college algebra, natural log of 1 is 0. So here I got 4,000 equaling to 0 plus natural log of 1 is 0 times the 200 will be 0 plus c. So that means c will have to be 4,000. So that means the cost function, c of x, will be this, 10x plus 200 times the natural log of x plus 1 plus 4,000. So that would be your cost function. Now, the other part of the question, they ask for the average cost per pair of shoes if 1,000 pairs of shoes are produced each week. So here they want the average cost. And when you're finding the average cost, that means c bar of x, which means the cost function c of x divided by x. And our cost function that we found not too long ago was this, 10x plus 200 ln of the absolute value of x plus 1 plus 4,000. that whole thing is divided by x. So C bar of x would be this. Each term in the numerator will be divided by x. So if I do 10x divided by x, I'll be left with a 10 plus that 200 ln of the absolute value of x plus 1 will be divided by x. And then plus that 4,000 will also be divided by x. Okay. So now, that will be your average cost function. So now we need the average cost per pair of shoes of 1,000 pairs of shoes are producing each week. So that means x is equal to 1,000. So C bar of 1,000 is equal to this. 10 plus 200 ln of x is 1,000, so it'll be 1,000 plus 1 divided by 1,000 plus 4,000 divided by x, which is also 1,000. Now let's go ahead and simplify some things around here with this expression. 10 plus 1,000 plus 1 is 1,001, so that will be 200 ln of 1,001 divided by 1,000 plus 4,000 divided by 1,000 would be 4. And this we'll have to type into the calculator. And they want this answer to 2 decimal places, by the way, since we're dealing with money amounts. So here we got 10 plus, well, I'll tell you what, let me do this 2,000 ln of 1,001 first, divided by 1,000. So it'll be 200, press the ln key, 1,001, close parentheses, divided by 1,000. Okay. Then I'm going to add 10 and 4 together. So it'll be plus 10 and then plus 4. To 2 decimal places, this will be approximately $15.38. Okay. So what I did was I did this part first. Came up with that answer, then add the 10 and the 4 to it to get $15.38. So that would be the average cost per pair of shoes of 1,000 shoes are produced each week. Okay, so that does conclude this video in section 5.2 dealing with integration by substitution. I will do another video that deals with just additional problems from section 5.2 dealing with integration by substitution. So do be on the lookout for that. In the meantime, feel free to reach out to me if you have any questions about any of the problems or examples that were discussed in this video.